I grew up in Corpus Christi, in the barrio, as they call it, the ghettos of Corpus Christi. My parents had very little education. My mom had only a second grade education. In fact, she was an orphan. My dad only had a fourth grade education. So education in my family was very minimal. I was the first to graduate from high school, and actually the first to graduate from a college. My road to NASA was not a straight line. When I was 8 years old, I was just happy to make a few bucks, shining shoes, and doing odd jobs. My SAT and ACT scores weren't all that fantastic, and what I did was I went soliciting to some junior colleges here in Houston, and one accepted me on a probation basis, and they said, make a better average in 4 classes and you can stay. And so I made an A and average in those 4 classes, and I went on to get a 2-year associate of electronic technology. Then I transferred over to the University of Houston. I was looking for a job. Long story short, I interviewed with NASA.
Hey, welcome to this episode of the show. Today's guest is George Salazar, retired engineer at NASA after more than 40 years working for it. Good to see you.
Here.
Absolutely. I'll let you share your background and your story to better understand where you come from and what you did for NASA. Today, I want to tell you about a book I'm reading. It's written by 25 veterans of the U.S. Armed Forces, all graduates of the Masters of Business for Veterans program at the University of Southern California. The book is called Veteran Stories of Transition and Transformation. It collects the personal stories of veterans written in their own words. Pick it up for yourself or a veteran you love. Check out the link in the description for 10% off.
All right, I'll give you a short summary of my the beginning of my life, if you will. And so I grew up in Corpus Christi, in the barrio, as they call it, the ghettos of Corpus Christi. My parents had very little education. My mom had only a second grade education. In fact, she was an orphan and was at an orphanage in San Antonio for several years until she was of age to leave with her sisters. My dad only had a fourth grade education. So education in my family was very minimal. I was the first to graduate from high school. And actually, I became the first to graduate from a college. From my immediate family. My road to NASA was not a straight line. Students say, well, what did you do? When you were 8 years old, did you want to come work at NASA? And I said, no. When I was 8 years old, I was just happy to, make a few bucks, shining shoes, and doing odd jobs, to buy magazines and toys. So I was somewhat of a mediocre student in school. I have to say that for the most part, I did like science the most than the other classes that I had. So fast forward, after I graduated from high school, I actually graduated the bottom 20% of the class. I did odd things in Corpus Christi as far as, let's say, working with my dad's donut shop. And then I also did other things as well. In terms of making a few extra bucks. But eventually, we sold the business, the donut shop business, and then moved to Houston. Now, in Houston, I worked various jobs from construction to, my gosh, selling books door to door. But it was time to let's say, grow up and finally find something that I wanted to do. And so I didn't want to go back to college. I wasn't completely clear what I wanted to do in college. With the help of my wife, I actually decided to try to get into a college. And the challenge was that my SAT and ACT scores weren't all that fantastic. Therefore, I had to pursue a different avenue. And what I did was I kind of went soliciting to some of the excuse me, junior colleges here in Houston, and one accepted me on a probation basis. And they basically said, make a B or better average in 4 classes and you can stay. And so I made an A and average in those 4 classes, and I went on to get a 2-year associate of electronic technology. Then I transferred over to the University of Houston. I initially started in technology, but I wasn't happy with, let's say, I didn't feel like I was learning enough. And so, luckily, I came across a group there at the University of Houston that said, if you want to be challenged, switch over to engineering. And so I did. And the funny thing was that I was learning that people in engineering that were not making it were transferring over to technology. And here I was in technology going over to engineering. And I said, boy, did I make a mistake here. But needless to say, I graduated from the University of Houston with a bachelor's of electrical engineering. During the time that I was getting ready to graduate, I was interviewing with various companies that they had job opportunities. One of them was NASA Johnson Space Center here in Houston. And so I was looking for a job. I had already a family at that time. And so I wanted to start working. Long story short, I interviewed with NASA. They liked that I had experience because during the time I was going to school at the University of Houston, I worked as an intern in a seismic exploration company, manufacturing engineering. And I also worked as an electronics repair technician for Canon calculators, repairing some of their business calculators and mini computers. And so that was actually beneficial because my GPA wasn't all that fantastic compared to some of the other students that we're interviewing with NASA. There were 4.0s and all that, but I think my experience was a big factor. So I came to work at NASA and started out as an electronics engineer and kind of gradually moved my way up. And I have to say that after a couple of years, I kind of was thrown into a major, let's say, challenge, if you will, that I was told I was going to be a subsystem manager for the Space Shuttle Modular Auxiliary Data System. And I also was going to be the project lead for a voice control flight experiment on Space Shuttle. At that time, voice recognition or automatic speech recognition, as it was called at the time, was fairly new technology. But we're looking at ways of exploring new let's say, human-computer interfaces at that time. So, long story short, I was leading. I was doing many things. I was also a design engineer for the voice control experiment. I was also the project engineer. I was also the systems engineer. I had multiple hats. It was great. It was a learning experience. Actually, that's when I started to learn becoming a multidiscipline engineer because I started learning things about, let's say, vibration, thermal control, materials, selection of materials. People don't realize that only certain materials can fly on a space vehicle because of a close confined environment. So you have to watch things for outgassing, toxic fumes, and things of that sort. So you had to be very selective on materials. So I became very much multidisciplined. I wasn't expecting that. I thought I was just going to be electronics engineer, and that was it. But then I started to get more into leading projects, and so I got into systems engineering, and I started to evolve even more. One of the first big projects that I did was the X-38 flight computer system, which encompassed five onboard flight computers that basically were voting system for controlling the X-38 spacecraft. And then I started to evolve even further, and I'm going to fast forward here, that I started to get more involved with human-computer interfaces. So over time, I became what they call the human-computer interface technical discipline lead for NASA Johnson Space Center. So I had the responsibility of involved with anything associated with what hardware touch the human or the human interface with the hardware. And so one of my first big projects was the cockpit avionics upgrade of the space shuttle. And that was over 200 engineers involved with that project. And then I moved into the commercial crew program, working primarily with SpaceX and Boeing in development of their commercial crew programs. And SpaceX was a little bit of a challenge because SpaceX is using touchscreen technology, which is fairly new technology, at least for spacecraft control. So there were some lot of hurdles to overcome to make that happen. I had to work with quite a few subject matter experts in different areas of computer control and working with SpaceX as well to get that system certified, as well as the Boeing system. Boeing system didn't do as well as the SpaceX system, but I understand in the last episode they're still in the running for flying the Starliner. And then I got involved with my last few years. I got involved with the Human Lander system. That's part of the Artemis program, which we're going back to the moon. And so I was responsible, again, for the human-computer interfaces for the SpaceX Starship, their proposal for landing humans on the moon, as well as Blue Origin's system, as well as it's very similar to the commercial program. commercial crew program where you had SpaceX and Boeing. Well, in the human lander system, you had SpaceX and Blue Origin, just so you can have all different options in terms of landing humans on the moon. And so basically, in a nutshell, my roles at NASA have gone from electronics engineer all the way to systems engineer, learning human computers interfaces, learning about the human element. I have to say that the human element was something that became fascinating to me in learning about the importance of factoring the human element into a spacecraft system design. In fact, myself and three other colleagues were instrumental in establishing what they call Human Systems Integration Employee Resource Group that basically fused human systems integration into the engineering process. And so we're very proud that because of our efforts, a lot of the NASA documentation in terms of developing spacecraft systems encompass a lot of that human systems integration effort that we did over the years. So hopefully that that.
Absolutely, that's a fascinating story, all the way from your childhood to your retirement at NASA. Did you have some of the favorite projects or challenges that you had to overcome over the years?
Well, I have to say that the first one was actually the voice control flight experiment. First of all, I was not familiar with speech recognition. I was not familiar with how to develop spacecraft systems for certification for flight. And then I had to learn, as I mentioned previously, things like vibration, mechanical vibration, shock, shock systems. I had to learn about thermal systems, and I took classes in that, but a lot of the classes were more theoretical than practical, and so I really learned the practical on the job. And so I felt like I was drinking from a fire hose. I was learning about all these different technologies as well as learning how to process, developing flight system and process that system in order to get certified for flying on the space shuttle. It's basically it's the systems engineering process, developing requirements, developing options, looking at the options and which one is the more optimum. Of course, you've got constraints of schedule and cost. So you have to be cautious about that and still try to meet the technical. And the technical was really challenging because speech recognition at the time was not all that robust, if you will. And so, we had to develop methods and ways of improving the speech recognition given the constraints of the hardware. So I got involved with human factors engineers. I got involved with materials engineers. And so all of a sudden, I got out of my world of electronics engineering and got into all these other different disciplines. And so it was a challenge. I have to say that I didn't sleep much, for many months, just trying to stay abreast of what I needed to do, what I needed to do next, who to contact. I was somewhat of an introvert. I thought I was just going to design circuits and, leave me alone. But, I had to get out and talk to the experts. I had to talk to the program managers. I had to, travel to Kennedy Space Center and learn what does it take to deliver flight hardware to Kennedy Space Center as well as installing it. But I do have to say that I guess maybe it's the most memorable because it was the most challenging for me at the very beginning. But I got involved very early on with astronauts. The first flight experiment was it was on STS-41 on October 1990, where Bruce Melnick and Bill Shepard used the voice command system for controlling and evaluating the use of speech control on the space shuttle's robotic closed-circuit television camera, as well, and using that for the robotic arm control. One of the things I was really, it's one of those 15 minutes of fame, was that Bruce Melnick recorded a session using our system, and he mentioned my name as part of the demonstration that was downlinked to the ground. And so it's a very memorable moment that I'll never forget. I had learned that astronauts very rarely will speak out a name of a person that did something for them on this particular mission. So I was very proud of that. So I have to say that the voice control experiment was somewhat dear to my heart.
And over 40 years, You probably saw a lot of changes and evolution in technology, especially with the things that you worked with specifically. What were the most exciting changes or technological leaps that you've seen over the years at NASA?
Well, one of them has been, going back to speech recognition, speech control. That one has made quite a few leaps. It still has its challenges. One of the things about the human voice, as we found out from doing those experiments, is that there's a lot of variability in a voice, and more so when you go into space. So one of the couple of things that happen at a minimum to the human body when you go into space is one, there's something called muscular atrophy, where your body actually expands a little bit. And that's why you hear that astronauts grow 2 inches. That's because there's an expansion because of the microgravity effect. The other one is there's no sinus strain because they're here on the ground. You have sinus strain, but up in space you don't have that. So all of a sudden you start clogging up. And if you've ever noticed some of the video taken from up in space with astronauts, whether they're on station or shuttle, their face looks a little bit bloated, and that's one of the reasons. So your voice is altered, and there's so many different variations of what can happen to the voice, and of course psychologically, your voice can change. You're depressed, maybe you're sick physiologically, and so those things change. So the technology now has done a little bit better job. I say a little bit better. It's not perfect yet. It's done a little better job of dealing with speech variability over the years. The other thing that has changed dramatically has been the processing power of computers from back in the days of the shuttle. Now you got AI, and you have some of these high-tech, high-performance computer systems that perform AI. But I do have to say that there's some challenges with that kind of technology, taking it up into space, and that's primarily associated with the radiation effects of that kind of technology. Early on, even more so, like in the Apollo program, the the distance between, let's say, miniature electronic components was very far away, and so the likelihood of getting hit by a high energy particle, galactic radiation particle, was very less as it is now, because this technology is so compact that a lot of these components have come closer together, so the likelihood of taking a hit is more, the probability increases quite dramatically. And so you have to deal with that now. Even though you got more computing power, you also have to deal with the effects of radiation. So the computing power is obviously something that has changed dramatically over the years. The other thing I have to say is obviously the software. You have from the traditional, let's say, software programming such as C, C++, now to AI, chat boxes and all this kind of stuff. Of course, there are some challenges associated with artificial intelligence. I can tell you that in the safety community, artificial intelligence is not well received. One of the reasons for that is because when you're developing a flight system, you're developing a system that's you're trying to make it as deterministic as possible. In other words, this is the way it's supposed to behave over time. Well, if you have software that's very deterministic, well, it's supposed to behave in this fashion, and so you can follow that. But with AI, and let's say adaptive AI, it's changing on you. So as it starts to change, how you how do you verify that the behavior hasn't gone south on you? And so those are some of the challenges that we're still dealing with in terms of AI. And so if you ever hear about AI in some of the spacecraft systems and satellites, they're actually doing some AI, but it's, let's call it non-critical. The critical stuff is left to the more traditional deterministic type system. So again, just kind of recap very briefly is one, speech recognition, and two, the computing power, and actually number three is the software now that's changed dramatically over the years.
And let's briefly talk about the future of space exploration and how you see it. What will probably happen in 10 years, in 20 years, in 50 years? Where do you see this is going?
Well, I'm hoping that the next 10 years, we land humans on the moon. Unfortunately, one of the challenges, more political than technical, is trying to maintain a certain budget to keep the projects going. forward. And that was one of the things that was different about the Apollo program was that it had continuous, let's say, support from Congress, and so they were getting the money that they needed, to make that program happen. So let's assume that they're going to get the budget. The challenges is trying to develop the technology that's needed to go back to the moon. I have to say that the SpaceX approach for a human lander system is quite challenging. It's a huge rocket, to land on the moon. It's like a 10-story building, if you will, that weighs quite a bit of a few tons. Compared to the lunar lander that landed back in the Apollo program. Actually, Blue Origin has a smaller version that's more, let's say, in line with the Apollo program. So we have to come up with better ways of using commercial technology. SpaceX uses quite a bit of commercial technology right now, but it's on low Earth orbit, which actually is an advantage because in low Earth orbit, the Earth's magnetic field protects a lot of the low Earth orbiting satellites and space stations from high galactic, high energy particles. Once you get outside of that magnetic field, all bets are off. You're dealing with some high radiation, galactic radiation. So you're going to have to figure out how you adapt commercial products to that kind of environment. And I can tell you that most commercial companies, like for example NVIDIA, and some of the IBM products, they're not interested in developing radiation hardened components. There's no money in it for them. They'd rather get into, their big money is gaming, right? They say they'll sell millions of those compared to onesies and twosies for space exploration. So there are some radiation hardened products that are out there. BAE Systems, for example, develops radiation hardened products, but they're not cheap. If you're talking about something, let's say, for example, there's a computer chip called a field programmable gate array that's probably about 2 inches by 2 inches square. If you buy a commercial version of it, it's probably about somewhere in the vicinity of maybe $100, $200. If you buy the radiation hardened version of that from BAE Systems, you're looking at somewhere around $75,000 for just one part. So it gets very expensive developing radiation hardened products, and sometimes you got to have that. If you look at the Mars landers, the Mars Science Laboratory as well as Perseverance, they use quite a bit of radiation hardened parts, and they're much slower than commercial. So there's some challenges there as well. So the future, it's going to be dependent on a commitment from commercial companies and the government to continue exploring and evolving a lot of this technology, and not just the technology, but also working with the human element and how you're going to deal with humans going into deep space, because that is also a major challenge too as well. The psychological effects of a human can affect their performance in operating complex spacecraft systems. And you can say, well, we'll just let AI do that. But you can't always depend on AI and autonomous systems. Case in point, Apollo 11 was supposed to be an autonomous landing, but when Neil Armstrong looked out the window and saw that the Eagle was about ready to land on some big rocks, he had to shut off the autonomous control system and take control of the spacecraft and land it safely in a more better area. So the human, again, is always important to be in the loop and not depend fully on autonomous systems, and very much dependent on the application. So in time, I'm hoping that, the next 20 years, we'll see humans going back to the moon, and also, at least at a minimum, sending a, let's say, uncrewed spacecraft around Mars to basically ring out a spacecraft system design in preparation for the next step, which would be a crewed version of a Mars lander or transport system to land humans on Mars. And there's some major challenges with Mars in terms of the environment. So we have to practice all that on the moon. And that's what the Artemis program was all about, is to develop the technology, the processes and procedures necessary for us to go to another planet. So you don't want to, let's say, climb a 300-foot hill, and then the following day you say, I'm going to go climb Mount Everest. It's a big change. So I'm looking forward to the next 10 to 20 years that at a minimum we land humans on the moon, and we have a small uh, lunar base there to start learning to live on another planet.
Great. And before we finish, I'll let you use these few minutes to either give a few words to the listeners, maybe something that we haven't had a chance to discuss yet, but you wanted to share that, or maybe some of the pieces of advice for maybe young listeners who are aspiring to work for NASA or to work in this industry.
Yeah, I mean, I have to say that again, as I mentioned previously, the road to NASA was not from a straight line, point A to point B, but it was all jaggedy. You know, I tell students because I do a lot of outreach. I'm in the vicinity of 20,000 plus students that I've talked to and lectured in some fashion or another in my career. You know, one of the things that I find very motivating for me is that sharing my story about my childhood growing up and overcoming a lot of challenges in order to come work at NASA is something that some students they are not aware of. You know, people like myself, and there's a lot of them like me. This I have found out in similar situations. But you know, the importance is to try to get that story out. And so I tell students that you know you're not a failure. In fact, you know I don't like to use the word failure. I like to use the word setback. The only time you fail is when you stop doing it, right? So you know, you think about learning how to ride a bike. You know, I can tell you, I can't tell you how many times I failed before I finally learned how to ride a bike. But that was not a failure. That was just a setback. So it's important for students to understand that a setback, you don't stop. Don't stop, especially if you have a dream, you know, that you want to do. I actually put all this together in my autobiography. I just finished an autobiography about myself, and I'm hoping to, you know, to get that out as much as possible and have students read it because it's something that I wanted to do. It was more so for my family, but also for people that are perhaps in a similar boat or situation that I was. So getting that story out lets them know that they're not alone. That you know the determination and the perseverance can lead to success.
Thank you for sharing all of this, the stories and the lessons, and your view of the future and the message. I truly appreciate that, and it was a great time speaking to you today.
It was my pleasure having me. Thank you very much.
Absolutely.